In these problems, we are using differentiation to look at the motion of a particle. And this is where derivatives have applications in real life that are useful and interesting. So the key thing to remember is that if you have a function that shows the position of something, where something is across time, um, the first derivative of position is actually speed. And if you think about that, that should make sense. Uh, the rate of change of position is your speed, how fast you're going. And your derivative is really the rate of change of that function. So if you have a position function, first derivative is speed. The derivative of that, the rate of change of your speed, is called acceleration. That's how fast you're speeding up or speeding down. And so that's the second derivative. There's even a third derivative. Well, there's as many more derivatives as you want, but a third one that people call jerk, that has to do with how fast your acceleration is changing. So you can find out all of this stuff about a function. If you have the position function, you can get all these other things by taking the derivative, which I think is kind of cool. In this particular problem, it says a particle is moving along the x-axis. Its position x as a function of time is given by the following. X of t is t cubed minus 4t squared. And that's for anything where t is greater than 0. So in the first part of this problem, it says let v of t denote the velocity. So velocity is another word for speed. So this is going to be our first derivative of the particle at time t. And let a of t denote the acceleration. That's going to be our second derivative. And of the particle at time t. Find the position, velocity, and acceleration of the particle at time t equals 3 seconds. So we want position, that's this function. We want velocity, that's going to be, well, I guess we'd write this as x of t prime. That's going to be 3t squared minus minus 8t. Okay, so there's our first derivative. So that's going to be our velocity function, and our acceleration function is going to be the second derivative of that. So we're going to get 6t minus 8. Now, to find all of these values, the position, the velocity, and the acceleration, we're just going to plug in the value for t in each of these. So the position is going to be 3 cubed minus 4 times 3 squared. So that's 936. 3 cubed is 27. So 27 minus 36 is actually going to be -9. So it's to the left of the origin there. How about the velocity at that point? So the velocity is going to be our first derivative. We plug in 3 again. We're going to get, so 3 times 3 squared minus 8 times 3. So that's 3 times 9 27 minus 24. So that's a velocity of 3. And our acceleration, we just plug it in here. 6 times 3 is 18 minus 8. So it's an acceleration of 10. These positive and negative numbers tell you something, and I think that's what the next questions are going to be about. Let's see what B says. Answer the following questions to describe the motion of the particle at time t equals 3. Where is the particle located? It's at an x value of -9, so that's to the left of the origin. Which direction is it traveling? The speed is positive, so it's going to be moving in a positive direction. Speed can be negative, or velocity can be negative too, and that means it'd be moving back the other way. But in this case, it's moving in a positive direction, so that's to the right. And our acceleration is also positive, so it's speeding up. So in this last part, it says, how can the particle's speed be described at t equals 3 seconds? I'd say the particle is speeding up. If acceleration, our third derivative, or our second derivative, sorry, was 0, it wouldn't be speeding up or slowing down. It would be at a constant speed. And if it was negative, then it would be slowing down. So that's a little bit of work with using the derivative and the second derivatives of a position function.